Welcome back, everyone. We're on section 10.10 now. We've been covering free radical reactions, and let's think back to adding to a double bond. And you guys learned that when you have HX, let's say X is Br, as an example, that this will add in a polar kind of reaction. So we didn't learn about radicals at the time last quarter. We learned about this dipole here and how the double bond is a nucleophile that attacks the hydrogen. And so this is electron rich, and it's going to make an intermediate that looks like a carbocation, like this. And the hydrogen is added here. And then you learned how the bromide ion that came off attacks here, and then we end up with this product there. And that's considered Markovnikov addition because we're adding the bromine to the more substituted tertiary carbon rather than the primary. And that all has to do with carbocation stability. Now, if we wanted the Br to add to the less substituted side, we did learn that you need to add peroxides to this. The reaction would look like this. We'd have HBr, and then you would add ROOR as some kind of alkyl peroxide. So R could be some kind of alkyl group. And usually this requires some kind of heat or a light, some energy to break the ROOR into two pieces. So usually light or heat is fine for that. So with these reagents, instead of Markovnikov addition, we would see anti-Markovnikov. So the Br will end up here instead of here. So let's write that down. Now we're at the point where we've been covering free radicals, so now we can actually write a mechanism for this reaction. So let's do that. The first thing is we need an initiator. And instead of Br2, we have HBr, but we have a little bit of peroxide in solution, and this is going to help us start the radical process. The reason why is this OO bond is fairly weak. So this is a great initiator with a little bit of energy or heat, light. We can break this homolytically. So that's going to look like this. So we're going to generate two oxygen radicals from this peroxide breaking in half. And so that's the first step. And then this peroxide is the initiator. It's sort of like a catalyst. It gets the radicals going. So once we make these radicals, it will react with the HBr, similar to how we've seen the halogenation reaction before. So I'm going to show HBr, and there's a reason why I'm going to use Br, so we'll talk about that. And then these two will come together, and I will generate bromide radical, just like I have in the past. Now keep in mind that rather than the Br coming in and making a bond with O, the hydrogen is the one that makes a bond with the O. And that's because hydrogen radical is not as stable as bromide radical. Bromine is bigger, more polarizable, so it can take on that free radical better than a small hydrogen ion can. So these two steps are considered initiation. That is, it shows us how we're going to start off our reaction before we even bring in the starting material. These are just how the reagents work together. Now that we're ready with the reagent here, we've got this bromide radical. Now we can do something with that. Okay, so what we have here is two different ways that the pi bond can react with the bromide radical. Either the pi bond will bounce over to here and then make a little bond with the Br, or it could bounce over the other way and then bond to the Br. Now, if it does that, we could end up with the Br here and a radical here, or we could end up with the Br here and the radical here. And just like how we sort of analyzed this back in the day, remember we could have the positive charge on the tertiary or the positive charge on the primary. We know on the tertiary is more stable because of induction, and the electron clouds donate into that positive charge if there's more R groups. Well, same thing here. We remember radical stability is based on carbocation stability as well, and the idea that the orbital is viewed as half empty. So the more R groups there are, the better. So we think that this intermediate is better. So this is going to be more stable than the other radical. And when this radical forms, then I know that I need the Br to attach here on the less substituted carbon. So this is actually the way that I want to draw the arrows. So what's interesting is that it's actually anti-Markovnikov addition that results in the more stable radical. So it's still the same idea as why this is Markovnikov is the more stable carbocation. And here, this is anti-Markovnikov to make the more stable radical. Sort of like the same underlying concept, but just a different outcome. Okay, now this is technically called propagation because I start with a radical reacting with my starting material, and I get a radical out of it. So this is going to be propagation, and then this will react further, and I'll get another radical. So let's see how we do that. Once I make this radical, I want to think about how can I make more radicals, okay? And then remember, propagation is where you keep it going, like a chain reaction. I make something that can then go back and react again and make more of stuff and make more stuff. So if you think about it, the initiation steps helped us make bromide radical. I need propagation to help me make more bromide radical. So how I do that is I make this tertiary radical, and then I look at what I have. I have HBr. I have a lot of HBr. That's my main reagent. Okay, so let's use some HBr and see what happens. Now if I use HBr, I'm going to have either the H react here or the Br react here. And if you remember, the H prefers to react there, so I could make bromide radical, which is better than making hydrogen radical. So that's what I'm going to do here, is I'm going to bring in my HBr, and we're going to react the H with this, and the bromide will come off by itself. So now you can see how we get the neutral compound here, which is not a free radical. Everything's all paired up now with the hydrogen being added here where the radical was. Okay, so that's my final product. But I also have bromide radical, which then can feed back into here. Okay, so that's why we have these two steps being propagation. Hopefully it'll be neater in your notes than in mine. And then our termination step, we're making product in this propagation step, and there is no hydrogen radical and alkyl halide radical that's going to collapse together because we're trying to avoid making hydrogen radicals. So there's no termination step that's going to give me the product that I want. It's already part of the propagation step. So the only termination step that's left is to look at the radicals that you're forming, which are these guys here, and they could crash into each other. But that's an undesired product, but it's still possible. So there are a couple of termination steps that are possible. Your book only shows one of them, which is that you're more likely to have a lot of bromide radical in solution as a result of using HBr. So bromide will get together with bromide radical, and these two will crash into each other to terminate into bromine molecules, Br2, which is what is possible and detected in solution. And then another possible termination step, any two radicals that you have can get together. So this guy here could potentially get together, and we could have bromine radical here react with that potentially to give you a small amount of this side product as well, which is the dibromo compound. But remember, we try to have a small amount of Br radical as opposed to HBr, and that's because Br radical is produced by reaction with the peroxide. So as long as we keep the peroxide down in concentration, you're going to have less bromide radical than HBr. And remember, it's HBr that adds to this radical. So you try to keep HBr high and Br radical low. Okay, so let's try a practice problem. We've got this alkene and HBr and peroxide. So a few things, you could write it out formally, like initiation, here are the steps, propagation, here are the steps, and termination, here's a possible step. But if you just need to think about how this reaction works without being so formal about it, you can just maybe work through some of this in your head. You've got the peroxide breaking in half homolytically, you've got HBr, then these two get together, and this makes bromide radical. And once you get bromide radical, that will react with the pi bond here. And then you'll want to form the more stable radicals. So I think I'll want this radical to form here and this to get together with bromide radical, bromine radical. Okay, so then we'll have that. So let's draw what happens there. Okay, so I'm going to end up with something like that, and then after that I want to think about how this gets the hydrogen. So I have more HBr in solution, so I'm going to use HBr, and I'll show how this gets together like that in the propagation step. Now think about where that hydrogen comes in. So remember, the geometry of this is more like sp2 with an empty-ish p orbital, right? And so that p orbital is planar. Okay, these guys are planar, trigonal planar here, and that radical is, let's say, in here. So when we combine these, that radical is either on the top or it's on the bottom. And so that H can come in from the top or on the bottom. And so if this was a chiral center, meaning I didn't have two methyl groups, maybe one was ethyl and one was methyl, so it's going to be chiral, then I would have both stereoisomers. So in this case, I don't see the stereoisomers because I have two methyl groups here and they're the same, so it's not going to give rise to a chiral center. But I will write them both out as if it were chiral. So I would write, okay, so I would write both of these, but it's not really chiral center, so I'm just going to write that they're actually the same thing. But if it was chiral, you would see both enantiomers. And then just a note, we usually use some heat or light to get this reaction started. So usually you would see some symbols like H nu and delta for light and heat, or one or the other. So just keep in mind that you often see that in the reaction as well. All right, so here's some practice with just recognizing where what you're going to add. These are all HBr and with some peroxide. So what will the final product be? Will it be Markovnikov or anti-Markovnikov? And as you do this, maybe think through the free radical mechanism. So think about the ROOR, peroxide breaks in half with the free radicals, they react with HBr, and then that reacts with the pi bond, and then where does the Br go? Go ahead and give some of these a try, and then we'll check our answers. Okay guys, we're back, and you just mainly want to think about stereochemistry as well. So first, all of these are anti-Markovnikov. So you put the Br on the less substituted carbon, so this one, and this one, and this one, that one. And then you want to see, does that result in something chiral? So here there's two hydrogens, so that's not chiral. This is not chiral, not chiral. Here, this is chiral. So remember, if you have a radical here, it can add, the new group can add on the bottom or the top. So you're going to get, Br on top or Br on the bottom. So you're going to get both enantiomers there. No chirality here or here. So it's really just one that you need to worry about here.